Hello, folks. Welcome back to MJ School of Mining and Geology YouTube channel. In today's session, we're going to be focusing on the most two important textures that we see in alkali feldspars. That is perthitic and antiperthitic textures. So we're gonna find that when we're looking into the two-component system with solid solution, a eutectic and a solvus. So please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. So basically, we have I think about two videos that we already produced for the phase diagrams. The first one, I think we're looking at the binary system, especially the plagiaries. Please feel free to go visit it. And we also looked into the eutectic and perthitic, okay, so phase diagrams, in phase diagrams. So you are more than welcome to also visit that. But most of the terms, liver rules, degree of freedoms, how to calculate, or how to read the liquid composition and other things that have been discussed in those videos. So, but here we just revising some of the terms. Like solid solution, for example, solid solution is when two things are they occurring together in a solution, all right? And a solvus, it's a curve separating one solid a feldspar from two solid feldspar. Okay, so and then the liquidus line, it's the line which separates the liquid from two things. All right, and then or if you don't want to say two things, but the boundary above which the system is completely liquid. So, but then the solidus line, it will be the boundary below which the system is completely solid. So these are just some of the terms that we should remind ourselves of. Okay, and then the new thing that we never really talked about in our YouTube is the Exsolution. That's why today we want to focus on how this Exsolution or how this unmixing affect or form these perthitic or antiperthitic textures. But now, Exsolution is a process where a solid solution becomes unstable upon cooling and unmixes into two separate mineral phases. I mean, this kind of cooling, it usually is slow cooling. So slow cooling usually like things to, unmix. Okay. But think of this. Think of liquid and oil. We know liquid and oil, they usually don't mix, especially in low temperatures. So now if you can you can try it. Take your liquid, take your oil, and then, just cold water, it's fine. Pour your oil in that, and then you'll see these things, they won't mix, and I'm sure you are aware of that. But if you're increasing the temperature, you are forcing these two things to now mix or blend because you are increasing the temperature. You are not forcing them to mix. So it means even if you were to decrease the temperature again, they are not going to unmix, especially during the slow cooling. So this analogy is what we're going to be using here today. So what happens is at high temperatures, all right, when we're looking at the alkali feldspar, for example, so the single feldspar, especially when it hit what you call the solvus line, all right, we start to see a separation. It was saying a single feldspar, which is containing the two things, all right. But when we reach low temperatures, especially at that solvus line, unmixing or separation started to take place, and then now that unmixing is what you call the Exsolution. And depending on which side you your bulk composition started. If your bulk composition started on the side of the orthoclase, it means orthoclase, it will be the host the host, and if you started at the albite side, it means albite is going to be the host. So whatever side that you start, if you start on the orthoclase, it means that the orthoclase will be the host, and albite it will be a lamellae. If you started on the albite side, albite will be the host, and orthoclase will be the lamellae. This is what we called Perthitic or Antiperthitic. Okay. So I'm not going to waste your time. I just want to introduce these things. So I just wanted this thing to be very quick so that we can get done with it. The Eutectic line, it's the horizontal line on a binary phase diagram at the eutectic temperature. All right, and we know the eutectic temperature is the lowest temperature at which a liquid can coexist with two solid phases. All right, and we know that because now we've got three phases in there. We'll be having liquid plus mineral A and mineral B. It means now we've got three phases. If we have got three phases, it means our degree of freedom is going to be 0. And if our degree of freedom is going to be 0, it means the system won't shift at that point. It won't shift at that point because now the temperature, like remember the degree of freedom, it tells us how the system behaves. So if the degree of freedom is 0, it means you are not going to change either the temperature or pressure. You are not allowed to change the temperature and pressure, all right, at that point in time, unless one of these systems or one of these components or phases get to be consumed. And if one gets to be consumed, now we'll be left with two, and then now the system can now start to move. Okay. So these are some of the things, but if you want to learn in detail all this Eutectic and of course also Perthitic, you are more than welcome to visit that video on our YouTube channel. So as cooling continues, once the system hits the Eutectic temperature, the liquid starts to crystallize to solid phases at the same time. So the temperature would remain constant during this reaction. Okay, it will remain constant. Okay, so the system stays at the eutectic point because because removal of latent heat keeps the temperature steady until all the liquid is consumed and or one of the phases finishes crystallizing. Okay, so analogy is like how ice melts at 0 degrees until all ice is gone. So the temperature won't drop until phase changes completely. So how the perthitic textures form. So at high temperature, we are having single solid solution, all right, or single feldspar. So at high temperature, so what we see is at high temperature, orthoclase and albite will mix together perfectly in one feldspar crystal. So it will mean we'll be having this one feldspar crystal, and in this one feldspar, for example, I'm not saying it's half a half, but for example, you'll be having orthoclase, K rich, and albite, which is sodium rich. Okay, but now this one, it's a single feldspar. So at high temperature, you are allowing these to coexist. You are allowing these to coexist together. It's like you're forcing them to occur together in one mineral phase, okay, or in one feldspar. So this is called solid solution. So you have just one feldspar that contains the sodium ions plus potassium, like I said, and this one is this, and then that one is that. So these ones, they are occurring together or evenly, okay? It could be in equal proportion. It forms in the single feldspar filled above the solvus. So it will be, if this is the solvus, then single feldspar, it will be here. This will be the single feldspar. So it means above the solvus, that's where we find this single feldspar. That's where this orthoclase and albite, they are occurring together. But once now you are lowering the temperature, when you're lowering the temperature, especially when you hit here at the solvus line, separation starts to take place. Remember, you're lowering the temperature, but that lowering the temperature, it has to be slowly. It has to be slow cooling. Okay? So as that rock cools slowly, the solid feldspar become unstable. This is very important. It becomes unstable, and if it's unstable, it's no longer happy in the conditions you are putting itself into. Then what will happen to that? What will happen is now unmixing start to happen. All right. Now remember it's unstable. All right. The if you think of atom, okay, if you think of an atom, and we have the arrangement of atom in within a unit cell. For example, let's just say this is our unit cell. Let's think this is our atoms. All right, so let's say for what am I doing? Okay, sorry about that. And then let's do this. So let's say this is our, okay, let's say this yeah, different atoms. Okay, so these are different atoms that are arranging themselves nicely. So say yellow, let's say this yellow, let this yellow be, for example, potassium, and then let that be let that red cycle be whatever, the sodium. Okay, so when this becomes unstable, so what is happening, they start to be vibration to start to take place. They start to remember they are no longer comfortable in the new conditions that you're putting themselves into. All right, then what will happen to them? They will try rearrange themselves so that they are now in the good conditions, or they start to become comfortable in the new conditions that you put them into. So now these atoms start to rearrange themselves. When they rearrange themselves, what you see is you'll find now that it's fine. No, let's yellow be sodium. Yeah. Okay, and then now these yellow, you will find them rearranging themselves like that. For example, they are rearranging themselves. Okay, and now these ones they'll just be like that. It doesn't matter however they were before. Okay, and they are dominant. They will be dominant. They will be dominant. So it means these ones, they are dominant. They are dominant, and they are case or these. So if they are dominant, it means they're gonna give us what you call the host. Whatever that is dominant is going to give us the host. It means it's it is taking or it's occupying the largest space. Then whatever that is rearranging themselves parallel or sub-parallel to each other, these yellow parts, which are sodium in this case, they are forming what we call lamellae. They are forming what you call lamellae, which they are sub-parallel or parallel to one another. All right, and these lamellae, they are occurring within the host. And this lamellae in this case, say for instance, they are these or they are albite. Okay, and then this is what you call the perthitic texture. All right, this is what you call the perthitic texture. In the dominant phase is the orthoclase, and then the albite is going to be, forming the lamellae. So that's why we're saying sodium and potassium now don't want to stay mixed anymore. All right, they don't want to stay mixed. So because they are uncomfortable, they would need to rearrange themselves. So they start to separate or solve into two different feldspars. So one is sodium rich, which is albite maybe, okay, and then forms a thin lamellae. Okay, then the other one, it will be K-rich, although it leaves by cortline, which remains as the host. That's what I've explaining. This unmixing happens when the rock crosses the solvus line, immediately when it crosses the solvus line, and it enters here. When I'm saying see the diagram, there's a diagram below, so don't worry about that. And then when it crosses here, then unmixing starts to take place. That's where separation or exsolution that to take place. And then, yeah, this one that we're explaining here, and that's what you call the perthitic texture. But I'm gonna show you using the phase diagram. So let's see what's going on here. So you first have to consider the side from which you starting. All right. So obviously, if you are starting towards the orthoclase, it means the host it will be orthoclase, and then the albite it will be the lamellae. But if you're starting on this, for example, in this case, when you're starting on the right hand side, all right, wherein you're having albite, then it means your albite will be the host, and the orthoclase will be the whatever. I hope you get the gist. But now, this is your bulk composition. I like naming my bulk composition X. This is your bulk composition. This is your static composition. All right. That's why 0, 2, 10, 20, 30, 40, say, say 38 maybe. That's when you're having, okay. Yeah. 38 of that, and the remaining will be that. So that is the bulk composition. It's fine. We're fine with it. This part, when we are lowering the temperature, you remember, and this is the first where we're starting to crystallize things, and then that's where we read our solid composition. Here we read it here, for example, that this we've explained it in the binary system. So it doesn't matter you start here or you start here. Well, these two is a typical example of what you call the binary system. So if you need to understand the how the liquid changes along the liquid line, or how the solid changes, how the solid composition changes along the solidus line, you are more than welcome to go visit that and also try to understand the path. All right. So this is on the binary system. So we have explained this using the plagioclase. So please visit that. So my concern is us starting here when we are here. So we have a single feldspar. That's when I told you that it's like we're having something like that, wherein we're having, per se, for instance, potassium and sodium. Okay. Then now, because the temperatures are high, you are forcing these things to, coexist together. They are stable. They like to associate themselves with each other. All right. But now, when you start lowering the temperature, immediately when you hit this line is what you call solvus line. Immediately when you hit this solvus line, that's where, especially when you cross it, that's where unmixing start to happen. So here we'll start to have unmixing. If you don't want to say unmixing, you can say separation. If you don't want to say separation, you can say exsolution. Exsolution here. Okay, that's where you start to have an exsolution. But immediately when you go down, that's where you start to have a perfect exsolution. Okay. But what do? You say, you look at the side that you started at. So you started on the side here, the orthoclase. It means that the dominant one here, the host is going to be the orthoclase. So orthoclase is going to be the host. Okay, or K feldspar is going to be the host, and then this one is going to be the taking the part here, the lamellae. Okay, because you can see if you say remember, if I need to read the composition of the orthoclase, I need to study this side. So it will be 10, 20, 30, 40, 50, 60, 70. All right. So okay, am I reading it correctly? Yeah, 0, 10, 20, 30, 40, 50. Okay. All right. Yeah. 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 So, and then if I need this one, I'll start from here, 10, 20, 10, 20, 30. Okay, yeah, like that. So if I can tell that K Feldspar is the host because I started on this side. But now, what happened is if you check over here, the dominant part, which is the host, is the orthoclase. And then as those atoms, when they are rearranging themselves, they're gonna pack themselves subparallel, okay, or parallel, or forming these thin stripes. And then we call these things lamellae. We call these things lamellae. And then we, it will be that of the albite. And then basically that's what perthitic texture is. So perthitic texture is wherein the host is the, or we find the lamella of the albite within the host of the orthoclase. And the opposite is true for the antiperthite. So antiperthite, it means you're gonna start here. So you'll put your bulk composition here. You put your bulk composition here. So for example here, so obviously means the host now it will be the albite, and then this one it will form this orthoclase, it will form the lamellae. So that one is called the antiperthite. I hope you follow. Should you struggle to understand these things, please, you're more than welcome to reach me. Okay. So let's now I would like us to look at the only the perthite root. The antiperthite, obviously, it's IJKH. So I'm not gonna focus on that today. So that is the path for the antiperthite, this one. So if I'm starting from this side, so obviously this one IJK, H, there will be for the antiperthite. All right, it will be for the antiperthite. But now, I'm not looking for that now. I wanted to use the root for and the perthitic texture. That's where in we following the path A, B, C, or A, C, B, D, E, M, G, and F. And then over here, I know you already know what this is the Eutectic. It's the Eutectic. This is wherein you are having the three things occurring together. We are having the melt in this case, as you can see. You are having the what do you call this, albite on your right hand side. You are having albite on your right hand side, and you're having orthoclase on your left hand side here. So this is what you call eutectic. And up to so far, you know that this line, it will be the, what do you call this, the eutectic temperature. Means that the temperature is called the lowest temperature at which the liquid could ever exist. Okay, is the system once it's here, it's going to stop here because the degree of freedom here, it will be 0. So the system, it won't move here. It won't move here because the temperature is constant. All right, so the system don't move here until all of the liquid is consumed. All right, it's consumed, or one of the phases get to be consumed. Okay, but all of the liquid, sorry, get to be or okay, all of the liquid get to crystallize. Yeah, but now that is F in this case, but I want us to focus on these parts. So parts A, path A, that's wherein you are having this one. This is wherein you are having the melt is 100%. The melt is 100% liquid. Then with a composition that is rich in orthoclase. Why is it rich in orthoclase? Because it's towards the left-hand side where orthoclase is. And so at this point in time, at point A, no crystals. At point A, what we see is no crystals have formed yet. No crystals have formed yet. And the other thing is that the temperature is above the liquidus, the temperature is above the liquidus line. All right. The temperature is above the liquidus line. But once you start lowering this temperature, when you start lowering this temperature here, that's where the first crystals will start to form. But we read their composition here because the composition of the solid, we read that along the solidus line. Composition of the liquid, we read this along the liquidus line. And of course, the composition of the liquid run along the liquidus line, and this of the solid run along the solidus line. These are some of the things that we discussed in detail in that video of the binary system. So I hope up to so far you understand. And D, that's where our last crystal starts to, that is the composition of the last crystal. Okay, so our last crystal is here, and our last melt will be here. So I hope you guys, if you visit that, you're gonna even understand more. Okay, but once things start to get to G, and when things start to get to G, things or the thing that we talked about, which is what did we call it? We said at G, what we realize is just below, is just below the solvus. It's just below solvus. Then the other thing that we know of this point is the single feldspar, the single feldspar phase starts to solve into two distinct feldspars, which is AB and AB rich and OB rich, but there's no such a things called EB, let's say albite and or orthoclase. Okay, that's what we see. So the system, it means now the system has reached the two solid feldspar field. The system has reached two solid feldspar field. This is two feldspar field now. Okay, and then of course, you guys always know that, which is why I'm saying that if you haven't yet visited our video on the binary, wherein we're explaining things like a lever rule. So at any point in time, say you are here, you'll be able to understand how much of the albite do I have, and how much, even if I'm here, you'll be able to do that using the lever rule. So now, if we check over here. We notice something that is very interesting. That is to say, we see that we have got we see this Carlsbad twinning. We see this Carlsbad twinning. So we know that, okay, sharp, I'm dealing with the key feldspars. All right, so I'm dealing with the alkali feldspars, maybe, if you want to put it that way. And then because I see this Carlsbad twinning, but if I saw polysynthetic twinning, I know that I'm dealing with plagioclases. Okay, this is how under the microscope you are narrowing this down. All right, and then alkali feldspars, I always see these things with laminations. I know that definitely I'm on the alkali feldspars. But now I want to know if I'm dealing with the perthitic or antiperthitic texture. Okay, I see these lamellae. Okay, I see these lamellae which are light. I see these lamellae which are light. See these lamellae which are light whitish in color. So I know that this one, it's albite, and then it means this host is the orthoclase. So this host is the orthoclase, and then I know that this is the perthitic texture. I know that this is perthitic texture. So basically, that's how perthitic texture came into picture. But last but not least, we also having the antiperthitic texture or antiperthite. So antiperthite, like I said, that's when you starting on the side um, um, with more of the albite and less of the orthoclase. So if you start there, it means antiperthite, like I said, is a reverse of the perthite. And then instead of albite forming thin bands inside the K feldspar host, now K feldspar forms thin bands inside the sodium rich host. I hope you understand. And then how does this happen? Obviously, exactly like how the perthite okay, that is to say, at high temperature, these things are in a solid solution and they are stable. But once you lower the temperature and slowly, it shouldn't be a rapid cooling, should be slow cooling. If you lower the temperature slowly, and then now these things they start to become unstable. That single feldspar becomes unstable. Now making sure that now whatever the two feldspars that we had, they now start to separate. They now start to separate. And then how do they separate? Because they are rearranging themselves. So when they are rearranging themselves, they separate. All right, they separate, and then now in this case, would have the the lamellae of the lamellae of the orthoclase were occurring inside the host of the albite, and this is what you call the antiperthitic texture. So that was a quick look into the perthite and antiperthitic texture, and of course, Exsolution, understanding the science behind the Exsolution and how these textures they come into picture. Not only that, but the role of the phase diagrams. Now, you agree with me that the phase diagrams they are very important in not only metrology but basically geology, right? Yes. So thank you guys for joining us today. If you are still struggling to get these things right, struggling to understand what's really going on, please, you're more than welcome to hit the comment in the comment section, and I will be pleased to assist. And I'm sure you know what I'm going to say. Until next time, cheers.